question. So to be clear, on line 4, what I'm doing is setting up the prototype for swap. I'm not so much defining it as I am declaring it. I'm telling C that, hey, look, up ahead, you should see a function called swap that takes these two inputs and returns this value, in this case, nothing. And down below, when I, line 16, have that same prototype followed by some brackets and some code here, that's where I'm defining swap itself. A good question, though. Another good question, why aren't we returning in this function? So often we'll see if we want to get some value back in, let's say, main, we have the function we call return us some value. In this case, though, swap doesn't need to return much of anything. In fact, its entire purpose is to have this side effect of swapping values in place. Because we give to swap the addresses of two variables in memory, we have it follow those pointers to where those values are and move them around a bit like this, so we don't need to return anything because swap already has access to that place in memory. We're going to move those two values around. All right. Other questions too? Question here, why would this work without the percent or the ampersand A and ampersand B, because swap is defined above? Let's see. I'm not sure if this is answering the question, but we do see here that swap is taking in these values, ampersand A and ampersand B. And it's important here that we actually give swap the address of these values, not the values themselves. If I said A and B here, I would now be passing by copy. I would say swap, take the value of A, which is 10, and take the value of B, which is 50, and do whatever you want with it. But in this case, beyond the fact that swap is expecting a pointer, if I were to do that, I'm not actually telling swap where my values currently are so it can move them around. I'm just giving it a copy of those values for it to do whatever it wants with. Here, though, I should make sure that swap is able to take in the address of these values so it can move them around right where they are. Another question, why don't we declare swap instead of prototyping it? So we do. So this is the prototype and declaration for swap. We're telling C exactly what swap will be, and down below we define it as well. All right, so that was a bit of a lot. And our goal here is to show you all what you can now do with pointers. Like, it's not so much interesting to kind of swap things around like this and like that, but what is powerful, what is fun, is actually opening up files, reading data from them, and writing data to those files, allowing you to write even more complex programs as you go. So here we'll talk about this idea of file I/O. And file I/O stands for file input and file output, how we can write data to files and how we can read data to files. So as a visual here, let's think about how we can both open and close files first. When we work with files in C, there's this idea of opening up a file and closing a file, similar to what you would do on your own computer. If you were to open up, let's say, a Microsoft Word document, you open it up, and later on, when you're done, you just close it, hit that X button, and it's gone and stored away. In a similar way, your programs can open and close files too. So there are two key functions here for opening and closing files in C. One is called fopen, which stands for file open, going to open up a file for future reading or writing, where reading is kind of looking at the data, and writing is like adding data or modifying data. And now fclose goes ahead and closes that file for us. And now there's a bit of a hint here, just saw in lecture a bit, and one you should keep in mind as well, which is you should always fclose all files you fopen. And I'm curious to get a sense of your intuition for this. Like, let's say why is it important that we always close files we open? Why do you think? I'm seeing to free up memory, which is a good idea. Why else? So memory isn't wasted. Another good idea. Maybe you won't be able to use the file later if you don't close it. preventing memory leaks, that is kind of like a ballooning program using more and more memory over time. These are all good ideas, and I think you could really draw a parallel between you working on your own computer and just always opening files, but never closing them. Like one, it would just be a mess if your computer, every time you open it, just had all these open files on it, right? But the other thing is that if you ever want to send that file to somebody else, you would better close it so they can modify it without you also modifying it at the same time. So generally, it's good practice to make sure you open files when you're going to use them and close them when you're done with them to save memory, and also to ensure that no two programs are opening a file at the same time. Okay, so let's get a visual here for how we can actually write to our file. So here we see an actual file on the right-hand side and some piece of syntax we could use to open that file. In this case, we're going to use the fopen function. So fopen takes two particular arguments or inputs. It takes the name of the file, and let's say this file here is called hi.txt, as we see down below. So it's a text file that just says hi on the inside. And now, fopen takes another argument, another input, which is r. That is the mode we're going to use to open this file. There are two modes, read and write. And so what do you think r stands for? Well, read. We're going to open this file just so we can kind of see what's inside of it. We can read some data from it. And now, what do you think fopen returns to us? Based on what you see on the left-hand side, what does fopen return to us? You could look at the type on the left-hand side here. So I'm seeing a few ideas. One is that it returns the contents of hi.txt, which is close but not quite. I'm seeing another idea that it's a pointer to the file in memory, which is a good idea. And I think we could get this intuition-wise if we said, well, it looks like we have this variable named f, and its type is file space star. And whenever we see type space star, well, we should assume that is a pointer to that type. So in this case in C, there is a type called all caps file, which is basically like a way of trying to access the file. It's a bit of a fancy type, but suffice to say for now, it allows you to access some file, and it has a pointer to that particular file type. Now, as a bit of an oversimplification here, you could imagine that this variable named f now just points to, let's say, this location in memory or this file we're trying to open. It points to the very beginning of that file. In reality, there is more going on underneath the hood, like there is a very special file type like we discussed. C tends to move some of the data of that file to its own program, but for now you could just think of fopen as returning to you the location of this file in memory so you can actually see where it's stored. Much like you trying to find a file to open it, you first have to figure out what directory is it in, where is it located, and so on. So questions then on fopen and how we can try to find files to open them with our own programs? Okay. A question, why do the modes matter? That's a great question. So here we see we're going to open hi.txt using the mode R, which stands for read. There's also the mode W, which stands for write, which allows us to actually write some data into the file, to change or modify it in some way. I would say for now, just keep in mind that fopen might do two different things. It might set up the file in different ways for reading and for writing. Because reading just requires us to look at that file and see what it is right now, whereas writing, we have to set up the entire process of being able to change that file in some way. You can also, I believe, have both modes together, able to read and write at the same time. There are also other kinds of modes you could look up as well in the C standard library. Okay, so here we're able to open up a file, and it's easy to close it simply using fclose and then giving fclose the pointer to that file. So here we see f pointing to this file, telling us where it is in memory. We can simply say fclose and give it the pointer to that file, and now that file will, afterwards, be closed. We can no longer read or write from it. Okay. But let's say along the way we do want to read or write data from our file. So let's get a visual now for what it means to read and write from a file. So often, one thing we'll see is having a file, a bit like this one, hi.txt, in our program on the left-hand side with some variable like text. And maybe we want to store whatever is inside this file in some variable. We want to get it into our program so we can modify it or use it in some way. Well, if we were to read this data, it's basically like taking a copy of some chunk of our file and putting it inside of our program. So here I see this text, hi. I'll take a copy of it and put it inside this variable called text. And now it's inside my program. I could use it, modify it as I wish. It's simply a copy of whatever is inside this file. But now if I want to write data or modify this file, you could imagine maybe I have some value, like what's currently in text, and I want to put that in the file. Well, I could write data by copying what I have in this particular variable and appending it, that is adding it to this file here. I'll take hi, and now I'll put it at the very end of this file. I've written data or added data to this file here. So what questions then on this visual for reading and for writing? Question on the syntax, I think, which is a good question. So we've seen how to open and close files with fopen and fclose, but now how do we actually add data to them and read data from them? So for that, we have two other functions, one called fread and one called fwrite. And more on these as we go, but suffice to say for now that fread lets us read data from a file into our program. And fwrite allows us to read data, or to take data from our program and add it to a file. Now in particular, there's a new vocabulary word here called a buffer. And a buffer is simply a place we can temporarily store some data in our program. So let's say we have a file, and like we saw before, I wanted to read, let's say, 3 characters from that file, HI exclamation point. I would have a variable which serves as a buffer, that is some place to store that data inside my program temporarily. So a buffer is simply some particular name for a kind of variable that stores often file contents. Okay, so let's consider then why we might even want to use this idea of a buffer. I'm curious what you all might think here. If a buffer is simply some place to store part of a file, not all of it, why would we use a buffer? And another way of asking this question is this: why might we not want to read the entirety of our file into memory all at once? Like, why do we need a buffer in this case? If the goal of buffer is to break our file into smaller bits, why might we need that? So I'm seeing this idea of like saving up memory, trying to use less memory overall, which is a good one. Let's see, trying to avoid overflow, which makes sense. Maybe we don't quite know how big the file is. Trying to avoid segmentation fault. So I'm seeing some themes here, and among them are this idea that maybe our file is really big. Like, we don't want to have that entire file loaded up at once and put into memory. That's a good idea. The other idea is we often don't know exactly how big a file is. So the best we can do is look at small bits of it, one at a time, until we get to the end of our file at the end of the day. So that's why I might want to use a buffer. It allows us to look at some particular pieces of our file and not the entire file all at once. So if we have this buffer now, it's worth asking, how could we get data into that buffer? And for that, we'll see this idea of reading from a file. So if I wanted to read from a file, there are really two questions I should answer. The first is, from where am I reading data? Like, what file am I trying to get data from? And then, where am I trying to read that data into? Like, what buffer am I trying to put it into? And it turns out that fread requires us to answer these two questions before it can do what we want it to do. So let's see one example of fread here. So this is fread, and fread takes 4 inputs, or 4 arguments. One of the first ones you might care about is this one, which is, from where are we reading data? From what file are we trying to read data? And for that, we give fread a file pointer, some way of finding the location of our file in the computer's memory. So for instance, let's say we have this file here. The pointer to that file is called f. I could run fread a bit like this, by slotting in f as that 4th argument. So now fread knows from where to get the data from this file. But the next question we said is, where is this data going to go? Like, where in my program should I put this temporary piece of data I'm going to get from the file? Well, in that case, we might have something like a buffer, and that is going to be the first input to fread. So here now is our visual. Let's say we have a pointer to our file called f, and we have some place in our program called buffer, some place to store this data. Well, we could then just call that variable buffer, and now when we call fread, we could say we want to read into the buffer. That is, that will be a pointer to some place in our computer's memory, some address we want to put that data in. So now we've seen 2 out of the 4 arguments so fread can function. Where are we getting data, and where are we going to put it in the end? So questions here as well. And we'll see some examples later on. A good question, so buffer is a variable. Buffer is a variable, and in this case it is the address of some place in memory where we want to store the file's contents. Good question. Okay, so now the next thing is, there are still 2 arguments we haven't yet defined. Like, what are these arguments? Well, it turns out that these 2 are answering these questions here, which is, what size is the block of data I want to read, and how many blocks do I want to read? So it turns out that files themselves are composed of individual blocks of data. So you could imagine, let's say, a text file, and now I want to ask you, what might be the file, what might be the individual chunks of a text file? If I'm storing some text, what do you think might compose those individual chunks of the file? How would you break up that file if I were to ask you to break it up into smaller pieces? You could certainly break it up into lines or sentences or so on, but I would argue maybe the smallest unit we could get is an individual character of text. So maybe a character like A, or a character like E. So we saw our hi.txt earlier had h, I, exclamation point. Well, that file is probably just 3 chunks of memory, each 1 byte long. H is 1 chunk, I is 1 chunk, exclamation point is another chunk. And we know that characters are 1 byte long, so we could probably assume that that text file is broken up into individual pieces, individual bytes in this case. So some files do have individual bytes that make them up. Other files, though, are a little fancier. So while text files might have chunks that are 1 byte long, you could imagine a file like an image that stores color. Well, to store individual pixels, it turns out each pixel needs about 3 bytes. And so we could probably best think of an image file as being broken up into not 1 byte chunks, but 3 byte chunks, a bit like this, visually. So as we read files, it's important we figure out, well, how big are the individual pieces of data that make up this file. In the case of a text file, it's those characters that are 1 byte long. In the case of an image, though, it's those pixels that could be up to 3 bytes long, as well to store all the possible colors that pixel could be. And the question is, how do we know that? Well, often you just know that from convention. So if you're working with text files, by convention, we store them character by character. If you're working with images, you were able to maybe look up documentation for, let's say, the .png or .bmp file type. It tells you that those pixels are stored in 3-byte chunks. So often you don't know yourself, but somebody else, the maker of that file, will tell you how their data is stored. A good question. So it stands to reason then, if we know how to break a file into smaller chunks, we need to answer these two questions, which is how big are those chunks and how many do we want to read at once? So let's answer that first question. What size are these chunks? And this question is in bytes. So if we're working now with, let's say, a file that looks a bit like this, maybe it's a text file, it has individual characters, we could say the individual chunks of this file are simply 1 byte long. So we could tell fread, we're going to read chunks that are 1 byte big, right? But now the next question is, okay, I know my file is made of 1 byte chunks, but how many of those should I read all at once? Well, we could say maybe we want to read 4 at a time, or 8 at a time, or 2 or 1 at a time, whatever it is. In this case, let's say I want to read just 4 bytes at a time, able to see my file in 4-byte sliding windows, if you will. So here, if I read 4 bytes, visually it looks a bit like this. I'm looking at my file here, and I want to read whatever is in these first 4 chunks. My pointer F points to the first one. I'll take out the first 4 and put them in my buffer. I've made a copy of them from my file into my program, and now my file pointer points at whatever is still left to read. So if I have some sentence here, maybe I'm reading it 4 characters at a time, I see those first 4 characters, my file pointer gets updated and points to the rest of my file. If I call fread again and again and again, I'll keep moving further and further and further and further down my file, 4 bytes at a time, 4 bytes at a time. So questions on this, whether visually or syntax-wise, this is our final call or usage of fread. And we'll see this in action in just a bit. A good question, how do we decide how many chunks to take out? Often, it will depend on a few things. So one is, how much memory do you want to use at any one time? So if you were to take a big chunk out of your file, that's a lot of memory to store in your program, perhaps. At the same time, maybe you care about seeing all that data at once. That would be a good reason to do that. If you don't, though, quite care about seeing all your data all at once, you could read things in smaller chunks just to make sure you're not using up too much memory at any one time. The other reason you might make this value smaller or larger is it tends to be a little bit faster to read things in bigger chunks, like to read like, let's say 100 individual bytes versus, let's say, like 10 bytes 10 times, for instance. Or to make it even simpler, it's easier to read 10 bytes all at once than it is to read 10 bytes individually over and over again. So that's a consideration as well, though probably not as much a consideration for the kind of work you'll do in CS50 in particular. Another question here, is F able to return to the beginning of the file after doing the reading? It is. There is a special function you would call to move the file pointer back to the top. So when you use fread, as we said before, this file pointer continues through the file, through the file, through the file, gradually getting to the end. When you get to the end, you have to kind of rewind it back to the top. And if you're familiar with this idea of like a cassette player, where you have like some tape that kind of goes and spins and spins and spins, that's kind of what this file pointer is doing. Starts at the beginning, spins all the way to the end. Once you get there, you have to rewind it all the way back to the very beginning. Or a VHS tape as well. Nice metaphor there, yeah. And then another question here, how do we find how many chunks there are in the file? Well, actually, I would argue you can't quite know at the very beginning. Like, your computer is able to tell you roughly how many bytes are inside a file, but if you were to write a program to find the size of a file that you didn't know beforehand, logically, the only way you can find the end of that file, or how big it is by starting at the beginning, reading byte by byte by byte by byte until you get to the end, and you'll notice, well, there's no more file left to read. And so often at the end of your file, you'll see a special signifier, maybe a null terminating character, or some other kind of special character called an EOF, or end of file character, that tells you there are no more bytes to read. But it's a bit like strlen, as we saw a bit in lecture, where you can't quite know how long the string is until you go character by character or byte by byte to the very end of it, and you see that ending character, like a null character or an EOF, end of file character. Good questions. Okay, so let's make this a little more concrete, and we'll write a program here to actually check what kind of type a file is. So one interesting fact about a file, let me find this problem right here, is that generally files have a signature of bytes at the very beginning that tell your program and tell you what kind of file it is. So for instance, a PDF tends to begin with these 4 bytes, or rather 4 bytes that represent these numbers when stored as integers. So 37, 80, 68, and 70. If you see 4 bytes at the beginning of a file that look like 37, 80, 68, and 70, that file, turns out, will most likely be a PDF. And other files have their own signatures that they can tell you what kind of file they are at the very beginning of them. So what we'll do is write a program that actually opens up any given file and tells us whether that file is a PDF or is not a PDF based on those first 4 bytes. So let's go ahead and do that. I'll go back to my program here, and I'll refresh the window so I'm able to set up my code space. And I'll wait for that to load. And while we do, let me ask what questions we have on this prompt here, if any, on file signatures. A question I see is, what happens if my chunk is bigger than the last bit in the file? A good question. So you could imagine, let's say, you're reading maybe 8 bytes at a time, and you get to the end of your file, and there are only 4 bytes left to read. Well, what might happen with fread is it actually won't read past the end of your file, and instead of giving you 8 bytes, it'll give you 4 back. And the cool thing about fread is that it'll return to you the number of elements it has read. So if you say, read me 8 elements, 1 byte of 1 byte size each, it'll return to you the number 8. If it successfully did that. If it only read 4, it'll return to you 4, or if it only read 3, it'll return to you 3, or 0, it'll return to you 0. So fread does have a return value that you can use to figure out, are you at the end of your file, or are you not? So I think here my code space is loaded, so I will get set up here, and we're going to finish this pdf.c program. So I will code pdf.c, and here I have the beginnings of my program. So the goal is to use pdf.c a bit like this, /pdf, and then typing in some file name, like let's say test.pdf. And my program will say, yes, this is a PDF, or no, it's not a PDF. So the very first thing I should probably do is figure out how I can get that file name. And it turns out that that file name is going to be the first command line argument to my program. So if I did ./pdf, test.pdf, I could access that file name using argv {1}, as we learned in a prior week. So here, I'll go ahead and write the following. I'll say that I'm going to write get a string called file name, and it will be equal to argv {1). So not the very first argument, which is PDF, this ./pdf part here, but the second part, which is test.pdf, right here. So now I have a string called file name. And now I have to try to open up that file. So what function could we use to open up a file? Any ideas? We could use fopen. So fopen allows us to open up a file, find where it is, and return to us a pointer to that file we can use in our program. So I'll use fopen here. And it turns out fopen takes a file name as its first input. So whatever file name is in argv {1), I'll give that as input to fopen, and I'll try to open that file using just the mode R for reading it. I don't want to modify the file, I just want to read from it. But now I have to keep track of the pointer to this file. So to create a file pointer, I can use this file star type and make sure I give it a name. In this case, I'll call it F for consistency, and I'll say I have a pointer to a file called F. It is of type file star, file pointer, and it is the result of calling fopen on some file name to open up that file and tell me exactly where it is in memory. Okay, so now with F available, I need to figure out how I can read from my file. But to read from my file, what do I need first? Thinking back to what we had seen earlier about fread, there are a few questions to answer. I think we know where we're going to read from, but what do we still need? Probably, as some people say, a place to read to. So we're going to read from our file, but now in our own program we need to have some space to store those values. So in this case, it's probably worth thinking about first, like we want to read into a certain place, but then again, how many chunks are we going to read and how big are those chunks? Turns out that a PDF is full of 1 byte chunks of memory, and we want to read the first 4, right? So one way we could do that is by reading 1 byte, 1 at a time, 4 times, or we could use an array and store those first 4 bytes back to back to back. So often, buffers will be arrays of values. And in this case, I'll try doing that. I'll make an array of integers, because we're going to look at those first 4 bytes in the PDF and think of them as integers and ask, is this equal to some value? Like in this case, 37, 80, 68, and 70, those first 4 bytes. So I'll create some space in my program to store 4 integers. And this, as we saw in prior weeks, is the syntax to do that. I now have an array called buffer that stores 4 types, and those types are int, back to back to back. Now, this is good, but not quite particular enough. So if you recall from lecture, we might have this idea of an integer being worth about 4 bytes in size, and notice here that, well, we want to read things in individual bytes, like 1 byte at a time, not 4 bytes at a time. So we're going to use an integer type, but a special kind of integer type. And that is one called a uint 8_t, which looks a little weird, but basically all this is doing is saying, I want not just the generic integer type, which is 4 bytes long. I want, in particular, an integer that is 8 bits, or 1 byte long, that is unsigned, that is only positive, and that as an entire thing is its own type. So uint 8t. This is essentially a particular kind of integer, and it comes as part of the standard int library here. So I only know this because I looked this up beforehand, But when you're reading files, you could look up what kind of type is best suited for reading data from that file. Turns out that is a uint8t for this particular kind of file. And in CS50, we'll tell you in advance what kind of type you should use when you're going to read from a particular kind of file. All right. So here I have my buffer. And now I need to ask how I could read into that buffer. Probably going to use fread here. And does anyone remember what the first argument to fread is going to be? We were answering 4 questions here. Where we're reading from, where we're reading to, and the first one is indeed where we're going to read to. So we're going to read into our buffer here. And the next question is, how big are the chunks? Well, they're 1 byte long, as we said before. The next question is, how many chunks to read all at once? Well, 4 to read all at once. And now we're going to read from our file pointer. So notice we're not doing file name, not the name of our file, but instead the file pointer, f in this case. So with that, we actually successfully have some data inside our buffer. We can prove it. So I will write a for loop here. For int I equals 0, I is less than 4, I plus plus, to go from 0 to 3 and read through our entire buffer. I'll print out whatever is inside that buffer as an integer, like this. And I'll say buffer bracket I. And then at the very end, I will close our file like this to make sure we're being safe with our memory. I'll make PDF, run ./PDF, test.pdf, and now we see those first 4 bytes in our file. I have another file here too. I could say ./PDF or ./test or ./PDF, and then test.jpg, I believe. Hit enter. And notice now these are very different values for this JPEG. So the very first 4 bytes are 255, 216, 255, and then 224. So we see here this kind of signature of what this file is telling us its type might be. And we said before, well, a PDF seems to have these first 4 bytes of 37, 80, 68, and 70. So questions here on how this is working. We first opened our file, created a buffer, used fread to read 4 individual bytes from that file, and then printed those out as we went. A question here on, does this apply to all file types? Generally, all file types will have some signature or some metadata that tells you what type of file they're going to be. A question, what if we used int instead of uint8t? I'm actually kind of curious about this too, so I'll try int here as well. I will recompile PDF. I'll do ./PDF test.pdf. That doesn't look as good. And I'm curious why you think this might have happened. What might have gone wrong? So remember that the reason we used uint8t is that it was the right size of value to use. So the key thing about a uint8t is that it is only a single byte big. A regular integer, though, is 4 bytes big. So here what we see is that we're trying to perhaps create an array of up to 16 bytes if an integer is 4 bytes long, but we're only going to read 4 of them into that particular buffer. So if we take 4 bytes and store them inside this buffer, well, we might not get the values we expect. And that's kind of why it's important when you're reading files to make sure you're using the appropriate types and getting particular about the kinds of types you're going to use. So I revert this back to uint8_t, which basically means an integer that is going to be always positive, that is 8 bits or 1 byte long. I can now recompile, make PDF, ./PDF, test.pdf, and I'll see the numbers as I expect them to be. And a good follow-on question here. This program is decent, but I wouldn't say it's quite all the way let's say safe. So you can imagine me doing this if I type in ./PDF and leave this last argument blank. Who knows what could happen, right? Because we're going to try to move beyond argv and access some value. So there is some more work to do here, which I'll leave up to you to kind of make sure we have the right number of command line arguments and so on. Other questions conceptually on reading and writing? A question on the underscore t here. So underscore t basically identifies this as its very own type. So it's kind of a convention here. And this is broken down into a few parts. U stands for unsigned, only positive. Int stands, of course, for integer. 8 stands for the number of bits used. We have 8. We have 16 as well. And then underscore t means all of that is its very own type. And a question here, what is the return value of fread? That's an interesting question. So why don't I try that out? I could say int blocks read, because I know fread returns to me the number of blocks that it did read successfully. So maybe I'll print out the buffer, and at the end, I'll also print out blocks read %i \n. I'll substitute blocks read in here like this. I will then make PDF and do ./PDF, test PDF, and I'll see I successfully read 4 blocks. If I got to the end of my file, I might see fewer, or I might see none at all. Good question. Okay. So I think this brings us close to the end of our section. So if I say in problem set this week, we get a lot more practice using fread and fwrite even. Before we go off to our own studies, I want to kind of remind you all of fwrite as well. And one handy trick here is that fwrite is basically the same ordering as fread. Notice we have buffer, size of the chunk, number of chunks, and the place to now write into. The only difference, as I just said before, is that we're now not just reading from the file into our buffer, we're kind of copying from our buffer into the file and appending, adding data as we go. All right. So that, I think, should hopefully set you up very well for this week. Feel free to reach out if you have any questions, and hopefully see you next time.
So, hexadecimal numbers, as if we need another base number scheme, right? Well, most Western cultures, as you probably are familiar, use the decimal system, base 10, to represent numeric data. We have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we need to represent values higher than 9, we can combine those digits using the notion of place value. So for 10, we have a 1 digit followed by a 0 digit, and we intuitively understand that what we're doing there is we're multiplying the first one by 10 and then adding 0 for a total of 10. Computers do something pretty similar, as you're probably familiar with the binary system, base 2, the difference there being that there are only 2 digits to work with, 0 and 1, and so our place values, instead of being 1, 10, 100, 1,000, as they would be in the decimal system, are 1, 2, 4, 8, and so on. Here's the thing, though. Those zeros and ones, especially if we're being computer scientists and we're doing a lot of programming, we're working with computers, we're going to be seeing a lot of binary numbers. And those zeros and ones in large chains can be very difficult to parse, right? We can't just look at a a string of zeros and ones and necessarily know exactly what it is. But it's still useful to be able to express data in the same way that a computer does. And so we have this notion of the hexadecimal system, which is base 16 instead of base 10 or base 2, which means that we have 16 digits to work with instead of 10 or 2. And it's a much more concise way to express binary information on a computer system. It's much more human understandable. So we have the digits 0 through 9, and then we also have these extra 6 digits, A, B, C, D, E, and F, which represent 10, our notion of 10, 11, 12, 13, 14, and 15 in decimal. Sometimes, by the way, you'll also see these A through Fs as capital A through F, which is the way I tend to do it. It's just my preferred style, but either is fine. They both represent pretty much the same thing. So why is hexadecimal cool? Why do we need to use this other additional base? We already have 2 and 10. Why do we need 16? Well, 16 is a power of 2. And so each hexadecimal digit, 0 through F, corresponds to a unique ordering or unique arrangement of 4 binary digits, 4 bits. And so in that sense, we can express very long, complex binary numbers in hexadecimal in a much more concise way without losing information or having to do particularly cumbersome conversions on those numbers. So as I just said, each hexadecimal digit corresponds to a unique arrangement of 4 binary digits. So the binary string 0000 corresponds to hexadecimal digit 0. 0110 corresponds to hexadecimal digit 6. And 1111 corresponds to hexadecimal digit F. If you're looking at this chart, particularly if you're looking at the left side of the chart, you can already see there's a bit of an ambiguity problem here, right? Decimal 0 is pretty much indistinguishable from hexadecimal 0 other than the fact that it's under a column that says hexadecimal, but we probably won't always have that column there. And so generally when we were expressing numbers in hexadecimal notation to clearly distinguish them from decimal notation, we usually prefix them with the prefix 0x. 0x means nothing in reality. It's just a clue to us as humans that what we're about to see or what we're about to have to start parsing is a hexadecimal number. Obviously for the higher digits A, B, C, D, E, and F, which correspond to 10 through 15, it's pretty unambiguous that that's a hexadecimal number. And in fact, any hexadecimal number that has letters in it is probably pretty obvious as a hexadecimal number, but still, for the sake of clarity, it's always a good idea to prefix every time you refer to a digit as a hexadecimal number by prefixing it with 0x. So binary, as we said, has place values. There's a 1's place, a 2's place, a 4's place, and an 8's place. And decimal also has place values, the 1s, 10s, hundreds, and thousands that we all may recall from grade school. And hexadecimal is no exception here, really. It also has place values, but instead of being powers of 2 or powers of 10, they're powers of 16. So when we see a number like this, we pretty clearly know it's 397, right? Well, if we see a number like this, we know this isn't 397 anymore. This is the hexadecimal number 397. It's not 397, it means something different because we're using powers of 16 as all of our place values instead of powers of 10. In fact, the place values here would be the 1's place, the 16's place, and the 256's place, which correspond to our idea of a 1's place, a 10's place, and a 100's place if the number was 397. But since it's 0x397, we have a 1's place, a 16's place, and a 256's place. Or a 16 to the 0 place, which is 1, a 16 to the first power place, 16, a 16 squared place, 256, and so on and so on and so on. So this number is really 3 times 16 squared plus 9 times 16 plus 7. I didn't do the math here, but it's not 397. It's much, much larger than that. Similarly, we could have 0x_ADC. Well, that's A times 16 squared, or if we translate that to our notion of decimal numbers, that's 10 times 16 squared, plus D times 16, or plus 13 times 16. And don't worry if you haven't memorized that D is 13 or anything like that. There's not too many of these letter digits, and it'll become intuitive pretty quickly. So again, this is 10 times 16 squared plus 13 times 16 plus 12 times 1, so 0x_ADC. So, as I said, every group of 4 binary digits corresponds to a single hexadecimal digit, and so it's actually really easy to change back and forth between hex and binary. If you have this long string of binary digits, all you need to do is start grouping them right to left as groups of 4, and then you can consolidate them into hexadecimal numbers, severely limiting the number of digits you have to process mentally. Instead of 32 zeros and ones, as we'll see in a second, you might be able to get it down to just 8 hexadecimal digits. It's a lot more concise. The charts a few slides back will help you to kind of figure out this mapping, though you'll, again, memorize it pretty quickly, and we'll go through an example right now. So if we have a number like this really large binary number, or what appears to be a large binary number, and the only reason I say that is because it's just it's a behemoth, right? There's just so many zeros and ones there. But we probably don't really have a sense of what the magnitude of this number really is. We don't have any idea what it would correspond to in decimal, and in fact, we won't even see what it corresponds to in decimal right now. But we might be able to express this in a way that would give us some more information about just how big this number is. So let's go through that conversion process. The first thing we need to do is we want to group these digits out into groups of 4, starting from the right and working to the left. Now, there happen to be 32 digits here, which means we have a nice clean break of 8 groups of 4. So we have now, and remember that each group of 4 here uniquely corresponds to a hexadecimal digit. So we'll start, again, building our number from the right and working left. Well, what's 1101? Well, we do the math out in our head. We have 1 in the 8's place, a 1 in the 4's place, a 0 in the 2's place, and a 1 in the 1's place. That's 8 plus 4 plus 1, which we would know as 13, but we probably wouldn't write 13 out because we're working with hexadecimal. We need to convert it to the hexadecimal equivalent of 13, which is D. 0, 0, 1, 1, well, that's a 0 in the 8's place, a 0 in the 4's place, a 1 in the 2's place, and a 1 in the 1's place, so that's 3. And we can keep doing this again. We have here 9, and then 11, but that's B again. We 1 in the 2's place, 1, 1, well, that's a 0 in the 8's place, a 0 in the 4's place, a 1 in the 2's place, and a 1 in the 1's place, so that's 3. And we can keep doing this again. We have here 9, and then 11, but that's B, recall, 2, 10, or A, 6, and 4. And so that very large string of zeros and ones at the top is more concisely expressed in hexadecimal as 0x46A2 B9 3D. Well, okay, we've learned a new cool skill. What's the point? Well, you might not use this all the time. As we're going to soon see, we use hexadecimal quite a lot as programmers, not necessarily for the purpose of doing math with it, but because a lot of times memory addresses in our system are represented in hexadecimal. And so it's a really concise way to express otherwise cumbersome binary numbers. And so again, you're probably not going to do any math with it. You're not going to be multiplying hexadecimal numbers together or doing anything weird like that. But it is a useful skill to have so that you can express and understand memory addresses and other ways of using data in C. I'm Doug Lloyd. This is CS50. Pointers. Here we are. This is probably going to be the most difficult topic that we talk about in CS50. And if you've read anything about pointers before, you might be a little bit intimidated going into this video. It's true that pointers do allow you the ability to perhaps screw up pretty badly when you're working with variables and data and causing your program to crash. But they're actually really useful, and they allow us a really great way to pass data back and forth between functions that we're otherwise unable to do. And so what we really want to do here is train you to have good pointer discipline so that you can use pointers effectively to make your programs that much better. As I said, pointers give us a different way to pass data between functions. Now, if you recall from an earlier video when we were talking about between functions. Variable scope, I mentioned that all the data that we pass between functions in C is passed by value. And I may not have used that term. What I meant there was that we are passing copies of data. When we pass a variable to a function, we're not actually passing the variable to the function, right? We're passing a copy of that data to the function. The function does what it will, and it calculates some value, and maybe we use that value when it gives it back. There was one exception to this rule of passing by value, and we'll come back to what that is a little later on in this video. If we use pointers instead of using variables, or instead of using the variables themselves or copies of the variables, we can now pass the variables around between functions in a different way. This means that if we make a change in one function, that change will actually take effect in a different function. Again, this is something we couldn't do previously, and if you've ever tried to swap the value of two variables in a function, you've noticed this problem sort of creeping up, right? If we want to swap x and y, and we pass them to a function called swap, inside of the function swap, the variables do exchange values. 1 becomes 2, 2 becomes 1, but we don't actually change anything in the original function, in the caller, because we can't. We're only working with copies of them. With pointers, though, we can actually pass x and y to a function. That function can do something with them, and those variables' values can actually change. So that's quite a change in our ability to work with data. Before we dive into pointers, I think it's worth taking a few minutes to go back to basics here and have a look at how computer memory works, because these two subjects are actually going to be pretty interrelated. As you probably know, on your computer's system, you have a hard drive or perhaps a solid-state drive, some sort of file storage location. It's usually somewhere in the neighborhood of 250 gigabytes to maybe a couple of terabytes now. And it's where all of your files ultimately live. Even when your computer is shut off, you can turn it back on and you'll find your files are there again when you reboot your system. But disk drives, like a hard disk drive, an HDD, or a solid-state drive, an SSD, are just storage space. We can't actually do anything with the data that is in hard disk or in a solid-state drive. In order to actually change data or move it around, we have to move it to RAM, random access memory. Now, RAM you have a lot less of in your computer. You may have somewhere in the neighborhood of 512 megabytes if you have an older computer, to maybe 2, 4, 8, 16, possibly even a little more gigabytes of RAM. So it's much smaller, but that's where all of the volatile data exists. That's where we can change things. But when we turn our computer off, all of the data in RAM is destroyed. So that's why we need to have hard disk for the more permanent location of it, so that it exists. It would be really bad if every time we turned our computer off, every file in our system was obliterated. So we work inside of RAM, and every time we're talking about memory, pretty much in CS50, we're talking about RAM, not hard disk. So when we move things into memory, it takes up a certain amount of space. All of the data types that we've been working with take up different amounts of space in RAM. So every time you create an integer variable, 4 bytes of memory are set aside in RAM so that you can work with that integer. You can declare the integer, change it, assign it to a value 10, increment it by 1, so on and so on. All of that needs to happen in RAM, and you get 4 bytes to work with for every integer that you create. Every character you create gets 1 byte. That's just how much space is needed to store a character. Every float, a real number, gets 4 bytes, unless it's a double precision floating point number, which allows you to have more precise or more digits after the decimal point without losing precision, which take up 8 bytes of memory. Long longs, really big integers, also take up 8 bytes of memory. How many bytes of memory do strings take up? Well, let's put a pin in that question for now, but we'll come back to it. So back to this idea of memory as a big array of bite-sized cells. That's really all it is. It's just a huge array of cells, just like any other array that you're familiar with in C, except every element is 1 byte wide. And just like an array, every element has an address. Every element of an array has an index, and we can use that index to do so-called random access on the array. We don't have to start at the beginning of the array, iterate through every single element thereof to find what we're looking for. We can just say, I want to get to the 15th element or the 100th element. And you can just pass in that number and get the value you're looking for. Similarly, every location in memory has an address. So your memory might look something like this. Here's a very small chunk of memory. This is 20 bytes of memory, the first 20 bytes, because my addresses there at the bottom are 0, 1, 2, 3, and so on, all the way up to 19. And when I declare variables, when I start to work with them, the system is going to set aside some space for me in this memory to work with my variables. So I might say char c equals capital H. And what's going to happen? Well, the system is going to set aside for me 1 byte. In this case, it chose byte number 4, the byte at address 4, and it's going to store the letter capital H in there for me. If I then say int speed limit equals 65, it's going to set aside 4 bytes of memory for me. And it's going to treat treat those 4 bytes as a single unit because what we're working with is an integer here, and it's going to store 65 in there. Now, already I'm kind of telling you a bit of a lie, right? Because we know that computers work in binary. They don't understand necessarily what a capital H is or what a 65 is. They only understand binary, zeros and ones. And so actually what we're storing in there is not the letter H and the number 65, but rather the binary representations thereof, which look a little something like this. And in particular, in the context of the integer variable, it's not going to just spit it into, it's not going to treat it as one 4-byte chunk necessarily. It's actually going to treat it as 4 1-byte chunks, which might look something like this. And even this isn't entirely true either because of something called endianness, which we're not going to get into now, but if you're curious about, you can read up on little and big endianness. But for the sake of this argument, for the sake of this video, let's just assume that that is in fact how the number 65 would be represented in memory on every system, although that's not entirely true. But let's actually just get rid of all the binary entirely and just think about it as H and 65. It's a lot easier to think about it like that as a human being. All right, so it also seems maybe a little random that my system didn't give me bytes 5, 6, 7, and 8 to store the integer. There's a reason for that too, which we won't get into right now, but suffice it to say that what the computer is doing here is probably a good move on its part to not give me memory that's necessarily back to back, although it's going to do it now if I want to get another string called surname and I want to put Lloyd in there. I'm going to need to fit 1 character. Each letter of that's going to require 1 character, 1 byte of memory. So if I can put Lloyd into my array like this, I'm pretty good to go, right? What's missing? Remember that every string we work with in C ends with \0, and we can't omit that here either. We need to set aside 1 byte of memory to hold that so we know when our string has ended. And so again, this arrangement of the way things appear in memory might be a little random, but it actually is how most systems are designed, to line them up on multiples of 4, for reasons, again, that we don't need to get into right now. But this, so suffice to say, after these 3 lines of code, this is what memory might look like. If it assigned me memory locations 4, 8, and 12 to hold my data, this is what my memory might look like. And just to be particularly pedantic here, when we're talking about memory addresses, we usually do so using hexadecimal notation. So why don't we convert all of these from decimal to hexadecimal notation, just because that's generally how we refer to memory. So instead of being 0 through 19, what we have is 0x0 through 0x13. Those are the 20 bytes of memory that we're looking at in this image right here. So all of that being said, let's step away from memory for a second and back to pointers. Here is the most important thing to remember as we start working with pointers. A pointer is nothing more than an address. I'll say it again because it's that important. A pointer is nothing more than an address. Pointers are addresses to locations in memory where variables live. Knowing that, it becomes hopefully a little bit easier to work with them. Another thing I like to do is to have sort of diagrams visually representing what's happening with various lines of code. And we'll do this a couple of times in pointers and when we talk about dynamic memory allocation as well, because I think that these diagrams can be particularly helpful. So if I say, for example, int k in my code, what is happening? Well, what's basically happening is I'm getting memory set aside for me. But I don't even like to think about it like that. I like to think about it like a box. I have a box, and it's colored green because I can put integers in green boxes. If it was a character, I might have a blue box, but I always say if I'm creating a box that can hold integers, that box is colored green, and I take a permanent marker and I write K on the side of it. So I have a box called K into which I can put integers. So when I say int K, that's what happens in my head. If I say K equals 5, what am I doing? Well, I'm putting 5 in the box, right? This is pretty straightforward. If I say int K, create a box called K. If I say K equals 5, put 5 into the box. Hopefully that's not too much of a leap. Here's where things get a little interesting though. If I say int star pk, well, even if I don't know what this necessarily means, it's clearly got something to do with an integer. So I'm going to color this box greenish. I know it's got something to do with an integer, but it's not an integer itself because it's an int star. There's something slightly different about it. So an integer is involved, but otherwise it's not too different from what we were talking about. It's a box. It's got a label. We're going to label this one pk, and it's capable of holding int stars, whatever those are. They have something to do with integers, clearly. Here's the last line, though. If I say pk equals ampersand k, whoa. What just happened, right? So this random number, seemingly random number, gets thrown into the box there. All that is pk gets the address of k. So I'm sticking where k lives in memory, its address, the address of its bytes. All I'm doing is I'm saying that value is what I'm going to put inside of my box called pk. And because these things are pointers, and because looking at a string like 0x80c74820 is probably not very meaningful, when we generally visualize pointers, we actually do so as pointers. pk gives us the information we need to find k in memory. So basically, pk has an arrow in it, and if we walk the length of that arrow, imagine it's something that you can walk on. If we walk along the length of the arrow, at the very tip of that arrow, we will find the location in memory where k lives. And that's really important because once we know where k lives, we can start to work with the data inside of that memory location. We're getting a teeny bit ahead of ourselves for now. The data inside of that memory location, we're getting a teeny bit ahead of ourselves. We can start to work with the data inside of that memory location. We're getting a teeny bit ahead of ourselves for now. So what is a pointer? A pointer is a data item whose value is a memory address. That was that 0x80 stuff going on. That was a memory address. That was a location in memory. And the type of a pointer describes the kind of data you'll find at that memory address. So there's the int star part, right? If I follow that arrow, it's going to lead me to a location. And that location, what I will find there, in my example, is a green colored box. It's an integer. That's what I will find if I go to that address. So the data type of a pointer describes what you will find at that memory address. So here's the really cool thing though. Pointers allow us to pass variables between functions and actually pass variables and not pass copies of them. Because if we know exactly where in memory to find a variable, we don't need to make a copy of it. We can just go to that location and work with that variable. So in that sense, pointers sort of make a computer environment a lot more like the real world, right? So here's an analogy. Let's say that I have a notebook, right? And it's full of notes, and I would like you to update it. You are a function that updates notes, right? In the way we've been working so far, what happens is you will take my notebook, you'll go to the copy store, you'll make a Xerox copy of every page of the notebook, you'll leave my notebook back on my desk when you're done, you'll go and cross out things in my notebook that are out of date or wrong, and then you'll pass back to me the stack of Xerox pages that is a replica of my notebook with the changes that you've made to it. And at that point, it's up to me as the calling function, as the caller, to decide to take your notes and integrate them back into my notebook. So there's a lot of steps involved here, right? Like, wouldn't it be better if I just say, hey, can you update my notebook for me, hand you my notebook, and you take things and literally cross them out and update my notes in my notebook, and then give me my notebook back? That's kind of what pointers allow us to do. They make this environment a lot more like how we operate in reality. All right, so that's what a pointer is. Let's talk about how pointers work in C and how we can start to work with them. So there's a very simple pointer in C called the null pointer. The null pointer points to nothing. This probably seems like it's actually not a very useful thing, but as we'll see a little later on, the fact that this null pointer exists actually really can come in handy. And whenever you create a pointer and you don't set its value immediately, an example of setting its value immediately would be a couple slides back where I said pk equals ampersand k. pk gets k's address, as we'll see what that means. We'll see how to code that shortly. If we don't set its value to something meaningful immediately, you should always set your pointer to point to null. You should set it to point to nothing. That's very different than just leaving the value as it is, than declaring a pointer and just assuming it's null, because that's rarely true. So you should always set the value of a pointer to null if you don't set its value to something meaningful immediately. You can check whether a pointer's value is null using the equality operator equals, just like you can compare any integer values or character values using equals as well. It's a special sort of constant value that you can use to test. So that was a very simple pointer, the null pointer. Another way to create a pointer is to extract the address of a variable you've already created And you do this using the ampersand operator, address extraction, which we've already seen previously in the first diagram example I showed. So if x is a variable that we've already created of type integer, then ampersand x is a pointer to an integer. Ampersand x is, remember, ampersand is going to extract the address of the thing on the right. And since a pointer is just an address, then ampersand x is a pointer to an integer whose value is where in memory x lives. It's x's address. So ampersand x is the address of x. Let's take this one step further and connect to something I alluded to in a prior video. If ARR is an array of doubles, then ampersand ARR square bracket I is a pointer to a double, okay? ARR square bracket I, if ARR is an array of doubles, then ARR square bracket I is the ith element of that array. And ampersand ARR square bracket I is where in memory the ith element of ARR exists. So what's the implication here? An array's name, the implication of this whole thing, is that an array's name is actually itself a pointer. You've been working with pointers all along every time that you've used an array. Remember from the example on variable scope. Remember all along every time that you've used an array. Remember from the example on variable scope. Near the end of the video, I present an example where we have a function called setInt and a function called setArray, and you're challenged to determine whether or not, or what the values will be printed out at the end of the function, at the end of the main program. If you recall from that example, or if you've watched the video, you know that when the call to setInt effectively does nothing, but the call to setArray does. And I sort of glossed over why that was the case at the time. I just said, well, it's an array, it's special, you know, there's a reason. The reason is that an array's name is really just a pointer. And, you know, there's this special square bracket syntax that make things a lot nicer to work with, and they make the idea of a pointer a lot less intimidating, and that's why they're sort of presented in that way. But really, arrays are just pointers, and that's why when we made a change to the array, when we passed an array as a parameter to a function or as an argument to a function, the contents of the array actually changed in both the callee and in the caller, which for every other kind of variable we saw was not the case. So that's just something to keep in mind when you're working with or pointers, is that the name of an array is actually a pointer to the first element of that array. Okay, so now we have all these facts. Let's keep going, right? Why do we care about where something lives? Well, like I said, it's pretty useful to know where something lives so you can go there and change it, work with it, and actually have the thing that you want to do to that variable take effect and not take effect on some copy of it. This is called dereferencing. We go to the reference and we change the value there. So if we have a pointer and it's called PC and it points to a character, then we can say star PC. And star PC is the name of what we'll find if we go to the address PC. What we'll find there is a character, and star PC is how we refer to the data at that location. So we could say something like star PC equals capital D or something like that, and that means that whatever was at memory address PC, whatever character was previously there, is now capital D if we say star PC equals capital D. So here we go again with some weird C stuff, right? So we've seen star previously as being somehow part of the data type, and now it's being used in a slightly different context to access the data at a location. I know it's a little confusing, and that's actually part of this whole like why pointers have this mythology around them of being so complex. Is kind of a syntax problem, honestly. But star is used in both contexts, both as part of the type name, and we'll see a little later something else too, and right now as the dereference operator. So it goes to the reference. It accesses the data at the location of the pointer and allows you to manipulate it at will. Now this is very similar to visiting your neighbor, right? If you know where your neighbor lives, you're not hanging out with your neighbor. You know, you happen to know where they live, but that doesn't mean that by virtue of that, having that knowledge, you are interacting with them. If you want to interact with them, you have to go to their house. You have to go to where they live. And once you do that, then you can interact with them just like you'd want to. And similarly with variables, you need to go to their address if you want to interact with them. You can't just know the address. And the way you go to the address is to use star, the dereference operator. What do you think happens if we try and dereference a pointer whose value is null? Recall that the null pointer points to nothing. So if you try and dereference nothing or go to an address nothing, what do you think happens? Well, if you guessed segmentation fault, you'd be right. If you try and dereference a null pointer, you suffer a segmentation fault. But wait, didn't I tell you that if you're not going to set your value of your pointer to something meaningful, you should set it to null? I did, and actually the segmentation fault is kind of a good behavior. Have you ever declared a variable and not assigned its value immediately? So you just say int x semicolon. You don't actually assign it to anything, and then later on in your code you print out the value of x having still not assigned it to anything? Frequently you'll get 0, but sometimes you might get some random number and you have no idea where it came from. Similarly, can things happen with pointers? When you declare a pointer, int star pk, for example, and you don't assign it to a value, you get 4 bytes from memory. Whatever 4 bytes of memory the system can find that have some meaningful value. And there might have been something already there that is no longer needed by another function, so you just have whatever data was there. What if you tried to dereference some address that you don't, there were already bytes and information in there that's now in your pointer. If you try and dereference that pointer, you might be messing with some memory that you didn't intend to mess with at all. And in fact, you could do something really devastating like break another program or break another function or do something malicious that you didn't intend to do at all. And so that's why it's actually a good idea to set your pointers to null if you don't set them to something meaningful. It's probably better at the end of the day for your program to crash than for it to do something that screws up another program or another function. That behavior is probably even less ideal than just crashing. And so that's why it's actually a good habit to get into, to set your pointers to null if you don't set them to a meaningful value immediately, a value that you know and that you can safely dereference. So let's come back now and take a look at the overall syntax of the situation. If I say int star p semicolon, what have I just done? What I've done is this. I know that the value of p is an address because all pointers are just addresses. I can dereference p using the star operator. In this context here at the very top, recall, the star is part of the type. It's int star is the data type. But I can dereference p using the star operator. And if I do so, if I go to that null, if you don't set them to a meaningful value immediately, a value that you know and that you can safely dereference. So let's come to a value that you know and the using what will I find at that address? Okay, so I said that there was another annoying, I will find an integer at that memory location. Okay, so I said that there was another annoying thing with stars, and here's where that annoying thing with stars is. Have you ever tried to declare multiple variables of the same type on the same line of code? So for a second, pretend that the code I actually have there in green isn't there, and it just says int x, comma y, comma z, semicolon. What that would do is actually create 3 integer variables for you, one called x, one called y, and one called z. It's a way to do it without having to split it onto 3 lines. Here's where stars get annoying again, though, because the star is actually part of both the type name and part of the variable name. And so if I say int star px comma py comma pz, what I actually get is a pointer to an integer called px and two integers, py and pz. And that's probably not what we want. That's not good. So if I want to create multiple pointers on the same line of the same type, int stars, what I actually need to do is say int star pa, comma star pb, comma star pc. Now, having just said that, and now telling you this, you probably will never do this. And it's probably a good thing, honestly, because you might inadvertently omit a star or something like that. It's probably best to maybe declare pointers on individual lines. But it's just another one of those annoying syntax things with stars that make pointers so difficult to work with, because it's just this syntactic mess you have to work through. With practice, it does really become second nature. I still make mistakes with it, still after programming for 10 years. So don't be upset if it's something that happens to you. It's pretty common, honestly. It's really kind of a flaw of the syntax. Okay, so I kind of promised that we would revisit the concept of how large is a string. Well, if I told you that a string, we've really kind of been lying to you the whole time. There's no data type called string. And in fact, I mentioned this in one of our earliest videos on data types, that string was a data type that was created for you in cs50.h. You have to pound include cs50.h in order to use it. Well, string is really just an alias for something called a char star, a pointer to a character. Well, pointers, recall, are just addresses. So what is the size in bytes of a string? Well, it's 4 or 8. And the reason I say 4 or 8 is because it actually depends on the system. If you're using CS50 IDE, char stars, the size of a char star is 8. It's a 64-bit system. Every address in memory is 64 bits long. If you're using CS50 Appliance or you're using any 32-bit machine, and you've heard that term 32-bit machine, what is a 32-bit machine? Well, it just means that every address in memory is 32 bits long. And so 32 bits is 4 bytes. So a char star is 4 or 8 bytes depending on your system. And indeed, any data types, and a pointer to any data type, since all pointers are just addresses, are 4 or 8 bytes. So let's revisit this diagram and let's conclude this video with a little exercise here. So here's the diagram we left off with at the very beginning of the video. So what happens now if I say star pk equals 35? So what does it mean when I say star pk equals 35? Take a second. Star pk. In context here, star is dereference operator. So when the dereference operator is used, we go to the address pointed to by pk, and we change what we find. So star pk equals 35 effectively does this to the picture. So it's basically syntactically identical to having said k equals 35. One more. If I say int m, I create a new variable called m, a new box. It's a green box because it's going to hold an integer, and it's labeled m. If I say m equals 4, I put an integer into that box. If I say pk equals ampersand m, how does this diagram change? Pk equals ampersand m. Do you recall what the ampersand operator does or is called? Remember that ampersand, some variable name, is the address of a variable name. So what we're saying is pk gets the address of m. And so effectively what happens in the diagram is that pk no longer points to k, but points to m. Again, pointers are very tricky to work with, and they take a lot of practice, but because of their ability to allow you to pass data between functions and actually have those changes take effect, getting your head around them is really important. It probably is the most complicated topic we discuss in CS50, but the value that you get from using pointers far outweighs the complications that come from learning them. So I wish you the best of luck learning about pointers. I'm Doug Lloyd. This is CS50. Struct car or struct student. That's a lot to type. have the ability to define our own data types. But if you've used structures, you know that sometimes using those data types can actually be a little cumbersome because we have to use the struct keyword when we're working with them. Struct car or struct student. That's a lot to type if we just want to have something simple like a structure. We want to be able to work with things a little more shorthand way like int or char, something a lot more convenient to type. Fortunately, there's a way to do this in C with something called typedef, which is a way to create shorthand or rewritten names for data types. You can rewrite data types that already exist, or you can write data types of your own. The first thing you do is you define a type in the normal way, and then you just alias it to something else. Typedef, old name, new name. Pretty straightforward, right? So we could typedef, for example, the already existing data type of unsigned char as byte. And then from now on, after we've made this type definition, again, which is usually going to be at the top of our .c files or in a .h file separately, we can just use byte everywhere we would have used unsigned char. That's a lot shorter to type. In CS50's library, we do this. We typedef char star as string because we abstracted away the idea of pointers and the fact that a string is really a pointer to the first character in an array of characters because it's just so confusing to get your head around that. But in fact, that's what we do, and this line of code actually exists in CS50.h, typedef char star string, just to make that a little less cumbersome to have to deal with. Already you've seen probably a little bit of the value here, but typedef becomes great when combined with structures, as I alluded to earlier. Structures have a two-word type name, and so they can be really annoying to create variables of that type or malloc size of struct something. Your lines can just get really, really long. And so you can use typedef to come up with something a lot shorter. So if I define a car as follows, I have my definition of a car, struct car, and then open curly brace, all the fields of my structure, close curly brace, semicolon. After I've defined my data type, I can typedef struct car as car underscore t. And then when I've done that, now every time I would have otherwise used struct car, I can just use car underscore t. That's a lot shorter of a way to express this idea of this structure that I just created. Alternatively, because structures are so commonly used in typedef, you can actually define the type in between the start and the end. So the typedef structure, again, is usually typedef, old name, new name, where the names are already types that you've created, but you can actually define a structure right in the middle of the typedef instead of having to define it separately and then do a typedef of it. And that would look just like this: typedef struct car, open curly brace, all of your field definitions, close curly brace, car t. So the old name is all of that stuff in red. You're just defining the structure and naming it at the same time. And then the new name is car underscore t. And so if we start to use this in code, previously I might have said struct car, my car, semicolon. Well, I don't have to do that anymore. Now that I've used the typedef, I can just say car underscore t, my car. That's a lot shorter. I can just say car under semicolon. Well, I don't have to code at the same time. And the name is open curly brace, all of your field definitions, close curly brace, car t. So the old name is named car underscore t, my car. That's a lot shorter of a way to do it, and in fact, it's going to be a lot more convenient, especially as you start to use structures a lot more in your code. And in car, we're defining the structure and to use, well, I don't at the same time. That's a lot shorter of a code. I'm Doug Lloyd, especially as you start to use structure. That's a lot shorter of a way to do it, and in fact, it's going to be a lot more convenient, especially as you start to use structures a lot more in your code. I'm Doug Lloyd. This is CS50.